In this video, we will be going over a brief introduction on substitution reactions. So one thing to mention briefly is that with a substitution reaction, we are referring to a nucleophile that substitutes for a leaving group. And so during these chemical reactions, nucleophiles attack a compound. Usually they are an alkyl halide because they have a halogen attached to the compound that leaves, and it serves as a leaving group. Now they serve as leaving groups because they actually are good leaving groups, meaning they are willing to leave from the compound after a nucleophilic attack and remain as a stable species after that. So first thing we want to talk about is substitution reactions, and we'll talk about SN1 in particular. So with SN1, we are referring to a unimolecular reaction. And remember, with unimolecular, if we go back into Gen Chem, unimolecular reaction, those are reactions that are determined experimentally, and when we are referring to them, we are referring to rates, and that goes back into kinetics. So with the unimolecular, we have a rate, and that is going to equal K, and it's multiplied by a concentration of a compound or some type of molecule. And in this case, if we are working with a unimolecular rate, we are going to have just one compound in question, and that's just applicable to organic chemistry, and that's pretty much what's going to make the difference between organic and Gen Chem, because now we are working with actual chemical reactions that involve nucleophiles and electrophiles. So now we can kind of demonstrate that here. Over here we will demonstrate a generic form of an alkyl halide, and actually we'll call this an R group, and we will attach it to X, and X will just be our halogen. So X can simply be chlorine, bromine, or another halogen. And so Rx, and then we will put a 1 right here, and that's just going to demonstrate that we are working with a unimolecular reaction. Now with SN2, we are working with a bimolecular reaction, and with that we are going to show that the rate equals K, and now we are going to have two chemical species that are involved in this reaction. So we will use our original alkyl halide, so we're going to use R and X, and then we will also be using a nucleophile with this reaction as well, and that's going to serve as bimolecular because we are working with two chemical species, whereas over here in SN1 we are just working with one chemical species. And by the way, these K's are supposed to be a lowercase k. Capital K indicates basically that you are working with equilibrium, and small k is indicating that you are working with kinetics. So I just wanted to point that out as well. Now the next thing is, if we go back into SN1 reactions, we are going to show our first step, which is an alkyl halide, as I've mentioned before. But remember, it's unimolecular, so we are only using one chemical species to determine the rate. And remember too that when we are determining rates, we are looking for transition states, and this double dagger just indicates that we are working with the delta G transition state. And so with those transition states, we are looking for the lowest step or the slowest step in the chemical reaction. And so from that we can see that if this is our starting point right here, and we have to climb this hill to reach this activation energy, we will see that this transition state is going to require much more energy than, say, for example, this transition state, because we can see that if we trace this back, we can see that it's at a lower level energetically than this first transition state. So from that, we are going to make this our rate determining step, and we can just classify that as RDS for rate determining step. And that's what we were referring to when we are looking at kinetics and when we are talking about rates. So for this chemical species, this one chemical species, we are referring to how it reacts on this transition state. And so what we are referring to now is, if we go back and we look at this molecule, we see that this bromine eventually gets knocked off and becomes a carbocation. Now I specifically made this carbon a tertiary carbon, and I did that for the reason of we want this carbocation to be stable, and remember, we can stabilize a carbocation through hyperconjugation, and so that's what we are going to do with these three carbons attached. And so why does the bromine just get knocked off? I mean, isn't that energetically unfavorable? That used to be a question I would always have, and basically through collision and as molecules bump against each other and move about through a solution, eventually one of these bromines, especially if you have a good leaving group such as a halogen, like in this case, this will eventually just get knocked off. And when that happens, you end up with the carbocation species right here, as indicated right here. And so then you end up with a situation where you have a nucleophile, and with that nucleophile you can come in from either side of the ring, or either side of the planar molecule. And in this case, we are working with a planar molecule because it's sp2 hybridized. And it's simply sp2 hybridized because it has a carbocation, and when we knocked a bromine off, we ended up with a planar molecule. So for that reason also, I want to mention that you are going to end up with a racemic mixture, just to add some more terminology to your vocab. So you end up with this racemic mixture, and that just basically means that you are going to have something that you should have theoretically equal amounts of product. So I should theoretically have 50% of a product that represents the nucleophile coming in from this side of the planar molecule, and I should also theoretically have 50% of a molecule coming in from this side of the molecule. And I do say theoretically because that's not always the case during a lab experiment. I mean, you might end up with like 60-40, 70-30, something like that, but we're just going to say for this example that we are going to have a 50-50 mixture. So now we can see over here that we have our nucleophile that's attached to the molecule, and now that it's attached, that's going to be our final product. And this is not going to be stereospecific either, because remember, we lost our stereospecificity when we created this carbocation. So we're not going to have to worry about demonstrating an inversion or anything like that. We just lost our stereospecificity with the carbocation. So now let's look at all of these steps and apply them to this Gibbs free energy diagram. And by the way, these Gibbs free energy diagrams are very useful in explaining how these interactions are taking place, and the explanations are very useful, especially when you're trying to relate things energetically to one another. And so over here we have this transition state where bromine it's not quite broken off yet, but it's getting very close. And we can see that we can pretty much apply this to, let's see here, we can use, let's try green. This is going to represent this part of the energy diagram, because once again this is very, very high in energy. And then this over here, this sp2 hybridized molecule, which has a carbocation, is going to be an intermediate. This intermediate is going to be represented right here in the energy diagram. And we'll just put a carbocation right there. And then we go through another transition state where our nucleophile is taking place, and it's attacking to the carbocation, and when that occurs, we end up with our second transition state right here, and then ultimately we end up with our final product, which is going to end up right there. And so, as you can see, that's how we translate an SN1 reaction to a Gibbs free energy diagram. Now, it's a little bit counterintuitive, because with SN1 you might think, well, it's just one, so shouldn't we just have one transition state? Why do we have two? And I guess it's just backwards to that. I guess that's probably the best way to think of it. And it's backwards to that because we are referring to how many species are involved in the slowest transition step. And by slowest, we are referring to the reaction rate, and we are saying that this is going to be the slowest step in the chemical reaction right here, because this takes more energy to climb this higher hill than it would to climb, for example, this hill right here on this second transition state. And so I just wanted to demonstrate that as well, and that's going to be applicable for SN2 reactions as well. And so let's just kind of think now about the SN2 reaction on the right hand of the screen. And so with SN2, we are referring to a bimolecular reaction, in which case we are involving two species. We are involving a nucleophile, and we are involving an alkyl halide. And so we are, like I said before, we're speaking in terms of the transition state, which is right here. And let me just put my double dagger just to indicate that. But basically that's my double dagger, and that's going to be my transition state, which is also going to be my rate determining step, as mentioned in the previous example. So now with my rate determining step, I can apply that to this step of the chemical reaction. And remember, by the way, when we started, we had a nucleophile, and it came in from this side right here. And I'm specifically showing it coming in from this kind of back side of the molecule. And that is going to be simply due to, if we were to, I guess, think about it in terms of molecular orbital theory, we could look at it as it coming in from the back side, because in this case we have what is called a HOMO on this side, and from the nucleophile, when it comes in, we have a LUMO, and those orbitals overlap. And let me just write that really quick here so we can make sense of it. So this right here is going to be our LUMO, which stands for lowest unoccupied molecular orbital, and that's located in the back side of this molecule. And then where the nucleophile comes into play, we are talking about it in terms of a HOMO. And that just represents highest occupied molecular orbital. And that's simply due to it. It's just due to it. It's because it has a lone pair attached to it, which we are indicating by this negative charge. And that lone pair is going to serve as a pair of electrons that are able to donate toward the LUMO side of the molecule that it's interacting with. And so I just wanted to address that, and in order for that to occur, it has to come in from this backside, as indicated with this drawing. So now the next step is going to involve a nucleophile in which it's getting closer to the molecule, moving in this direction, while bromine is trying to leave. So you could maybe think of it in terms of the bromine taking its electrons with it and trying to leave, but it hasn't quite left yet, and that's why it's part of this transition state or high energy level, which is located right up here relative to the starting point. So as it leaves, we end up with inversion, and so what does that mean? Well, if we were to take this molecule that we started with, and let's just say it had an R or S configuration, well, what we would end up with would be opposite to that. Now in this case we just have hydrogens, so those hydrogens aren't necessarily going to indicate whether we have an RS configuration at the end of our final step, but if we did have a chiral carbon in the beginning, we would end up with with an opposite configuration to that. And one way to think of it is, if you have an umbrella and it's during a snow, or you're in a tropical rainstorm, for example, and I'll just try to draw a little umbrella. But if you have something like this, and you go through a tropical rainstorm, you may end up with an inverted umbrella, and that inverted umbrella will probably look something like this, where you have now something that looks like this, because we'll just assume that the wind blew this umbrella and inverted it in the opposite direction, as indicated right here. And so anyway, that's just kind of the analogy to this inversion step that takes place during an SN2 bimolecular reaction. So anyway, this is SN2, but as mentioned earlier, it is a little bit counterintuitive, because with 2 you think, okay, well maybe there should be 2 transition steps, but really there's only 1 in this case, and that is indicated right here. And that's just simply because when this nucleophile came in and attacked this alkyl halide, the bromine left, and it did so in a concerted process. So I might as well write that too. So this was all concerted. And so by concerted process, we are just going to have 1 transition step, and from that we can see that our final product is going to be right here. And so that is the difference between an SN1 and SN2 reaction. Now in our next video we can talk about the differences and how we determine good leaving groups, poor leaving groups, good nucleophiles, poor nucleophiles, so on and so forth, and then we can go from there and differentiate between different ways that these interactions could occur. And by the way, before I forget, I also made these hydrogens attached to this molecule instead of methyl groups, and I did that intentionally because I didn't want to show that we would have carbocation formation. And with carbocation formation, remember, we need some stability in order to help stabilize that carbocation. Well, when you just have hydrogens, or when you have a primary carbon, as shown here, you're not going to have that effect. And so that also helped with our bimolecular reaction and prevented us from showing a carbocation. So we will demonstrate more of this in our next video.